Hello everyone. Thank you for watching this video. Um, Today, my internet connection in my office is not very stable. I think it's due to maybe this bad weather outside. So I keep dropping the internet, and I'm not able to deliver the live lectures. So that's the reason we switch to record this video, and you just watch this video. And then, so for the lectures on Monday, I will also quickly go through today's video in the beginning of the Monday's class. All right, let's start. On the Monday, right? Last Monday, and we introduced the concept like how to calculate the different ways of the motions of the fluid particles in the differential form, right? And we finished how to calculate the particle acceleration of the particle, so that it turns out that the acceleration of the particle can be calculated by the material derivative of the velocity field. Okay, and we also introduced how to calculate the the rate of the rotation of the particle, right? And the rate of rotation, we denoted as omega. Okay, basically that is rate of the change of the angular angle, okay, of the rotational motion of the particle. And this omega can be the vector form. It can be three components, okay, on the rectangular coordinates. And we also notating the sign of this omega as the counterclockwise the rotation as a positive value, and clockwise rotation as a negative value, right? And we're using this picture to try to derive that the correlations between how to calculate the omega from the velocity field. Okay, and this picture actually not only showing the how to calculate the rotational angle. It's also showing that how the angle is changed due to the angular deformation. Okay, and this 1/2 delta alpha minus delta beta is the change of the angle due to the rotation, okay, through a small delta t. And we have delta alpha minus delta beta. The reason you have this minus delta beta is because that if you look in this change of this delta beta is on the clockwise direction, okay, and delta alpha is on the counterclockwise direction. That's why you have the negative sign for the delta beta. And after we find this how to calculate this change of angle due to the rotation, and we also try to calculate the delta alpha, delta beta from the velocity field, right? This delta beta, delta alpha can be calculated from this delta eta and delta psi. Okay, and it turns out that this delta eta, delta psi can be given by the local velocity of these 2 points here. Okay, so that delta alpha will be delta eta over delta x. Okay, delta alpha will be this delta eta over the delta x. So this is like the arc length here of delta eta over the delta x, and delta beta is the delta psi over this delta y. Okay, and delta alpha, delta eta, and delta psi is calculated by the UVW as these 2 points here. These 2 points here, and the UVW of these 2 points can be calculated based on the Taylor series of the known value UV at this origin point. Okay, so we get the correlation, and then if we want to calculate the rate of the change of the rotational angle, right? This is the rotational angle. The rate of change is using this one divided by delta t and make the delta t equal to 0. Okay, substitute this delta eta, delta psi into it. We finally get the correlations between the rate of rotational motion omega with the velocity field. What's the correlation between them? So if we know the velocity field uv, for example, on the xy plane, we can calculate the omega z on the z, and this is z component of the omega vector. Okay, by using this way, we can also rewrite. So if we write all the 3 components, okay, on the xy rotation on xy plane, rotation on the xz plane, rotation on the yz plane, add them together, we can write this the overall form of the omega vector. Okay, and we also can able to write this omega vector in the vector form. We define a new vector we call the curl operator. Okay, this curl operator is defined as using this nabla, do the cross product with the vector velocity, velocity vector field. Okay, and so that the omega will be equal to 1/2. Okay, the curl of the vector of the velocity vector. All right, and so this omega will showing you that how the rotational motion will be, okay, or how fast the rotation of the fluid particle. And one thing we emphasize a lot during the last lecture is that we need to be careful that there is a difference between a particle is subject to a circular motion with the particle has a local rotational itself. Okay, we draw this kind of picture as an example. Okay, so if we have a particle and their streamline is circular, but the particle itself, okay, may do not any rotation, have any rotation locally itself. Okay, so during this motion, we call it circular motion. The particle, their phase, their direction, for example, the direction of this particle is not changed. There is no rotation for this particle locally. Okay, although this particle is moving circularly. So in these cases, omega is going to 0. All right. There is also a kind of motion like during this circular motion, if this particle itself also has a local rotational. When I say the local, is that this means that this particle is rotating, around some axis locally to this particle. Okay. For example, in these cases, you can see that at this time, this phase is going up, but at another time, this phase is going left. So if you're looking at this particle locally, so this particle is moving, it has a rotation on this, counterclockwise direction locally for this particle, moving up to right, okay, to the left, and to right to down. Okay, so in these cases, omega is not equal to 0. Okay, so be careful about the two cases. Okay, and also that from the definition of the omega, right, you see that we have this 1/2 of the curve of the velocity vector, right? Sometimes we do not like this 1/2, so we define a new parameter to represent the local rotational motion of the particle, and this parameter we call is the vorticity, and the vorticity is just equal to 2 times omega, which is just the curve of the vector field, velocity vector field. Okay, and in the Cartesian coordinate, right? The vector, the curl I vector can be written in this form, and in the cylindrical coordinate, the curl of a vector it can be given by this form. Okay, and the last one, the last parameter we introduced for related to the rotational motion is the circulation. Circulation is a scalar. Okay, and is defined as the integration of tangent velocity over the curve the particle is moving. Okay, so if it's a closed contour, okay, C must be a closed contour. So this is the gamma, and this is a scalar which is different with omega and vorticity. Both are the vector for those cases, for those two parameters. Okay, and so we're using this as an example. So if we have a very simple cases, right, the particle has a closed contour in this rectangular shape. Okay, we can easily prove that the overall gamma value integration on this rectangular path will just equal to this value. And if you take a close look of this value, this is just the omega z, which is this is just not omega z, sorry, the z component of vorticity. Okay, this is the z component of the curve of the so this one is just this cross of v on the z direction. Okay, so this is z, so this is the psi of z. Okay, so this is psi of z. Okay, so this is the z component of this vorticity. Okay, so in turn, so we based on this observation, we're showing you, we knowing you that okay, the circulation, which is the closed contour integration of the tangent velocity on the path, can be just equal to the area integration, which is integrated on the z direction of the vorticity over all the areas. Right? We have a contour integration, okay, of v vector, and then we can change this closed contour integration to an area integration, which will be the curve with this v vector on this normal direction of this surface, okay, which will be z direction, and integrated on the area, on the whole area. And this area A is all the area inside this closed contour. Okay, and on the mathematics, okay, on the math theory, okay, how the way we change this contour integration to an area integration is called the Stokes theorem. Okay, so this is also called the Stokes theorem in the 2-dimension. Okay, so this function giving us that instead of just when you try to calculate the circulation, right? Instead you do this line integration, we can just do an area integration if we know that the all the circulations, all the vorticity is inside. So this is vorticity. Okay, but okay, there's a very very important limitation for this theorem. If you want to use this theorem, you change from the contour integration to the area integration. Okay, so your v vector, your v velocity field inside this contour region must be continuous. Okay, in another word, what you may ask me that what does this continuous mean, right? In another word, okay, inside this contour region, your v velocity field should not have any singularity point. And again, what is singularity point? Okay, so if your v will be equal to x1 plus y, okay, then x equals 0 is the singularity point, because that when x equals 0, when x equals 0, this goes to infinity. It's a pole. Okay, so this 1/0 is called the singularity point. Okay, so so let me emphasize this again. This equation can only be used when you have no singularity point inside the integration, this contour. Okay, if you have a singularity point, for example, if I have a point here is singularity, this one is not working. Okay, so if you want to use this one, you make sure that there is no singularity point inside. Okay, and to illustrate this, let's use an example problem to do that. Okay, and we have flow field, and this flow field is in cylindrical coordinates, and we have the r, is actually on the r theta domain. Okay, and there is no radial direction velocity, and velocity is only on the theta direction, so only the tangent direction you have the velocity, and the v theta is only a function for r. Okay, and so let's assume that this fluid particle is moving on a circular curve. Okay, because we have the circulation there, and let's consider two cases. The first case is that when you have a rigid body rotation. The second case is that if we can see that if we can find the FR so that the flow becomes irrotational. What the irrotational means which means that omega z equal to 0 on this r theta plane. Okay, and so let's try to start it. First, let's write what's the vorticity. Okay, so this is only on this is the cylindrical coordinates, right? We only have r theta flow on the r theta on r theta domain, right? So we only need to find this z component for the vorticity. Okay, so let's go back to this expression here. We're only interested on the z direction. Okay, we're only interested on this one. And remember that the VR is always 0, so this term is gone. So the only thing left is this term. And v theta is only a function of r, so you have a value for it. Okay, so this z direction component of the vorticity just equal to this one. Okay, so the z direction vorticity is just equal to this one, which will be also equal to 2 times omega z. Okay, of this one. All right, and let's consider the first cases. If the fluid moving with the flow field is like a rigid motion, rigid body rotation. What does this mean? Okay, in the rigid body rotation, which means that this fluid is moving like a solid, right? So everywhere their tangent velocity it just can be given by v theta equal to omega r. It's omega is angular velocity of this rigid body rotation. It's a constant. Okay, and this v theta is given by their local radial r value. Okay, you substitute this v theta value for this rigid body rotation back to this equation here to calculate what is this z direction vorticity value component will be. Okay, and you can calculate it. You can show you that this z direction component vorticity is just 2 omega. Okay, and also now you go back to looking at this velocity field, right? Remember that Vr is always 0, v theta equal to omega r. So if you look at this velocity, there's no singularity point inside this flow domain, right? Because omega r, right? There's no singularity point. Okay, and so in this cases, which means that we can use the Stokes theorem, so that if we want to calculate the circulation, right, this gamma integration on the velocity times this ds, we can just change it to an area integration, right? Change it to the psi z, which will be 2 omega over dA, and because this omega is constant, you can take it out, so that your gamma will just be equal to 2 omega a. So this will be the circulation if you have any, closed contour to do integration on this flow field. Okay, this is for the flow with the rigid motion. And the second case is that where we want that is if we can find a flow field so that there is flow become irrotational. What the irrotational means? That means that omega equal to 0, right? And this is the omega. Remember what we found. And so for irrotational flow, this omega has to be equal to 0. And we can just solve this differential equation. It turns out that this v theta, r times v theta, has to be constant if you integrate this form, this equation on r. Okay, and yeah, another word, v theta has to be in the form of a constant divided by r. Okay, so it's telling us that if this v theta is in this function form, a constant any arbitrary function c over r, then the omega z will equal to 0, so flow becomes irrotational. Okay, and then in these cases, okay, if we want to calculate gamma, how we can calculate it? If we want to calculate the circulation. Now let's take a look at this velocity field. Vr equal to 0 and v theta equal to c over r. Now you see that we do have a singular point for the flow field. The singular point is r equal to 0, because when r equal to 0, this c over r, when r equal to 0, this c over r, you will go to infinity. So you have a singular point. When you have a singular point, remember when we talk about this Stokes theorem, when you have a singular point, you won't able to use this anymore. Okay, so you cannot using the Stokes theorem anymore, and you just do the contour integration directly. Okay, so this is v of theta of r, and the integration on the ds. Okay, so if you do this contour integration, this small ds here will be just equal to r times d theta, right? This is r, and this theta change of d theta, and then you integrate theta from 0 to 2 pi for the whole contour. Okay, and you turn out that your circulation is 2 pi of c. Okay, and for this case it is very special. The second case is the flow is irrotational, omega z equal to 0, but gamma is not equal to 0. Right? So let's go back to our previous discussion, right? You need to be careful about the two cases where you have the the particle do a circular motion with the particle do a local rotational motion. Okay. For the first cases, when you have a rigid body rotation for the fluid field, okay, this is when omega is not equal to 0. This is the cases that you have the local rotational motion for each particle. Like in these cases, you see that for the particle, this blue arrow, okay, the direction of these blue lines, blue arrows, okay, that keep changing. So they have a local rotational for the fluid particle. So that's why omega is not equal to 0. For the second cases, omega equal to 0. But okay, but the streamline of the flow is still circular. Okay, so this is the cases where we mentioned earlier, right? The flow has a circular motion, right? Because that is the phase, the direction of the particle, it won't change. There is no local rotation for each particle, right? That's why that omega equal to 0. Okay, but for both cases, the circulation gamma is not equal to 0. right? For this case, it's gamma equal to 2 omega a. For this case, it's gamma equal to 2 pi c, right? So now let's go back to this gamma here, the circulation. So you can see that the value of the circulation basically coming from the contribution of two parts. The first part is the rotational motion, the circular motion of the particle. The streamline has a curve, circular. The second contribution is that the rotational motion, the local rotational motion of the particle. Right? Both cases will contribute to the gamma. Okay? So the meaning of the gamma and the meaning of omega is not directly same. Okay? Because for this one, okay, gamma will not equal to 0, but omega will be equal to 0. Irrotational flow, but gamma is not equal to 0. Right? For this one, both gamma and omega will not equal to 0. Right? Okay, so just be careful about the different meaning of this omega and gamma and vorticity. Okay, just be very careful about these two cases, where you have the rotational flow, okay, and the irrotational flow, but with the circular motion. They are really different. Okay, now we finish talking about the rotational motion. Okay, and the next topic is talk about the deformation of the fluid particle. Similarly, okay, we also want to calculate the fluid deformation, deformation of the fluid particle from the velocity field. Okay, and we have two kinds of particle deformation. The first kind is angular deformation, and the second kind is linear deformation. Okay, for the angular deformation, okay, actually we already talking about this when we're talking about the rotation of the particle, rotational motion of the particle. Okay, we're showing you that the deformation, okay, the angular deformation, the change of this angle of the particle due to angular deformation actually is delta alpha plus delta beta. This is the angle, the total change of the angle due to the angular deformation. And remember that we have this correlation here. Delta alpha can be calculated by this one, and related delta alpha, delta beta can be related with the velocity field by this way. Okay, we can also calculate the rate of the change of the angular deformation. Okay, delta alpha plus delta beta over delta t, and make delta t equal to 0. So this is the rate of angular deformation in this xy plane. And similarly, okay, we change delta alpha, delta beta to this delta sigma, delta psi, delta eta, and then this delta psi, delta eta is related to the velocity field. And at the end, we can calculate that okay, this rate of angular deformation in the xy plane actually will be equal to partial v, partial x plus partial u, partial y. Okay, and similarly, you can also calculate the rate of angular deformation on the yz plane and the zx plane. Yz plane will be partial w, partial y plus partial v, partial z. And on the angular deformation on the zx plane, the rate of it will be equal to partial x plus partial u, partial z. Okay, and here again, okay, we give you the mathematical correlation that how to calculate the angular deformation on 3 directions, x, y, z directions, okay, by using the known velocity field. So if you know the velocity field, you can use this correlation to calculate what's the angular deformation on xy plane, on yz plane, on the zx plane. Okay, so this is the angular deformation. Okay, and we have an example problem to show you that how to use this angular deformation. Okay, and in this example problem, we have a flow, between the two plates. The bottom plate is stationary, and the top plate is moving with a constant velocity big U. Okay, and the flow inside is considered that we only have the x direction velocity. Okay, v is only have the component on the I direction. Okay, and also this x direction velocity here is only a function of y. It's not changing with x direction. Okay, so in these cases, okay, let's define 4 local points A, B, C, D. These 4 local points. Let's assume their position is given at t equal to 0. Okay, so the question is that after we know this velocity field, okay, after t equal to 1.5, what their new location will be. Right. So for this case is like we are going to track the fluid particle for each one, right? Actually, if you want to find this particle in their new location, you have to using a Lagrangian way description of the velocity field. Okay, and but the velocity field here given is the Eulerian way. Okay, but it doesn't matter. Why? Because that the velocity, because we know that flow is only have the u direction velocity and they have no v velocity direction, right? So we knowing that after this t equal to 1.5, all these 4 points is only moving to the right. It is not moving up or down. Okay, it's only moving to the right. So we and also that this u velocity, right, is x direction velocity only depend on y. Okay, and then for each particle during this motion, okay, because for this particle A, particle B, particle C, particle D, okay, during this motion, because it didn't change on their y value, this y value is not changing, okay, for this particle when they're moving. So they will have a constant velocity moving to the right, right? For this A will has a constant velocity moving right by calculate from y of A. B will has a constant velocity moving to the right with a constant value of y of B. Okay, so by this way, okay, we can just forget about this Eulerian Lagrangian descriptions. Okay, just knowing that for each particle they will move in constant velocity going to right, and then we calculate what velocity for each one by using their y location of each point, and just times this t value, we will knowing that how far they are moving to the right. Okay, for example, for this particle B, okay, you substitute this y equal to 3 over here. Okay, you can get the velocity. You can get the times. You can get the u velocity, x direction velocity of it, and then times this delta t 1.5. You knowing that okay, after 1.5 second, this B particle B will move to the right to this distance 4.5 millimeter. Okay, and similarly you can do for each other 3 particles. Okay, so that you can get that what the new location after t equals to 1.5 second of all these particles will be. Okay, you will see that this is A prime, B prime, C prime, D prime will be the new locations. Okay, and you see that B will move further to the right, right? But because that B has a larger y velocity, so we know that the velocity for the point B on the x direction is larger than velocity on the D. Okay, and A and C, their distance between them it will not change, because that we know that both A and C their velocity is same, right? Because they have the same y value. So that this line here and this line here will have the same size. Okay, and to calculate the angular deformation, so this is xy plane, right? So we just need to using this correlation here, partial v partial x plus partial u partial y, and because that velocity is only on the x direction, right? So v will obviously equal to 0. Okay, and then using u partial y, so this is u here, big U over y over h will be small u. So that partial u partial y will be u of 1 over h. Okay, you substitute it into it. So you know that, okay, the rate of angular deformation for this flow is 1 per second. Okay, and similarly, you can calculate the rotation. Okay, omega of z is 1/2, partial u partial v partial x minus partial u partial y. And because v equal to 0 again, v is gone, and u partial u partial y give you u over h. And you calculate it, you know that this is 0.5 per second. Okay, and so this example problem showing you that how to calculate the angular deformation from the velocity field and also the rotational one. So for this one, you've excited this omega z will get a negative value, which means that your flow, so the flow, because omega is not 0, right? So flow is rotational, and it's negative means that the flow is going to likely to move in clockwise. So you can know in that, right? Because this top plate is going right, right? It's like to drag the flow like in this way, right? Drag the flow to going this way. So it's like a counterclock, like a clockwise rotation. So that's why for omega they have negative sign. Okay, and for the angular deformation, you get a positive value because that when the this rate of angular deformation larger than 0, that means that the flow particle will become more skewed. Okay, and this is true because that when you try to move the top of plate, you like to make your flow inside more skewed. Okay, has larger gradient, have to create the velocity gradient on the y direction, right? So this is an example to show you the angular deformation. Okay, and the second deformation is the linear deformation. So what is the linear deformation? Let's go back to our decomposition of the flow, the motion modes. Okay, remember this is a decomposition, of the motion modes, right? So this is a linear deformation. So basically, linear deformation is that on the x direction or the y direction, the fluid particle will be stretched or contracted. Okay, and when will this stretch contracted happen? Let's focusing on this x direction. Okay, let's assume we have this face here and with this face here, and if the velocity on this face and the velocity on this face they are the same, then no matter how many times elapse, okay, the distance between the 2 points, these two faces will not be changed. So there's no linear stretch or contraction on this x direction, right? So yeah, in other words, okay, so if you want become this, for example, become this dashed line, right, on x direction, this particle is actually stretched. The only possible way is that is this the face, the surface here, the u velocity of this face is larger than u velocity of this face, so that this face is moving to the x direction faster than this surface, so that it is stretched. So in other words, okay, this x direction stretch is only happen when partial u partial x is larger than 0. Okay, and on the other hand, if you look at this one, okay, on the y direction, actually the particle is stretched, right? Sorry, not stretched, sorry, it's contracted. Okay, so the particle is contracted. The only possible way is that the v velocity, the y direction velocity on this surface is much be smaller than the y velocity on this bottom surface, right? The v velocity v1 here, v2 here, v1 must be smaller than v2, so that this surface moving to the on this y direction is slower than this surface moving on this y direction, so that when the time going on, this particle on the y direction will be contracted. So in other words, so this is only happen on partial y, partial v, partial y smaller than 0. Okay, so based on what we observe here, so we can get a conclusion for the linear deformation. So for linear deformation, okay, the element will change the length in x direction only if partial u partial x is not equal to 0. Right? If partial u partial x larger than 0, the particle will be stretched on x direction. Partial u partial x is smaller than 0, which means that on the x direction, the particle will be contracted. And similarly on the y direction, okay, the element will not change the length on the partial v partial y not equal to 0. And on the z direction, if there is a linear deformation, if and only if partial w partial z is not equal to 0. So basically, this partial u partial x, partial v partial y, partial w partial z itself will give you whether or not you have the linear deformation on the x, y, z direction. Right? So this will give you the result. Okay. But sometimes, okay, what we're focusing on is not whether or not the linear deformation happens or not. Actually, sometimes we are more interested than that. I know that you may have the linear deformation, but we are more interested on what about the volume or area. For example, I take the 0, right, on this linear deformation. So this is the area of this fluid particle. And after this linear deformation, you have another area inside this dashed line, right? And sometimes we want to see that how will the change of this area for the 2D cases or volume in the 3D cases of fluid particles. Then we can define a new parameter, okay, which is called the volume dilation rate. Where is it? Okay, so let's define a new called the volume dilation rate. Okay, partial u partial x plus partial v partial y plus partial w partial z. You add all these three together. Okay, and this is in the vector, using vector operator, this is just the divergence of the velocity vector. The divergence of velocity vector means that using this nabla operator, do a scalar product with this velocity field, v vector. Okay, and so this gives you that how the rate of the change of the volume of this fluid particle. Okay, so this is called volume dilation rate. So this is the rate of change the volume of this fluid particle. And for incompressible flow, right? What does incompressible flow mean? For incompressible flow, you have rho equal to constant. right? Rho equal to constant. And so because that we know that due to the mass concentration, we need to make this dm equal to constant, right? And what dm we calculated equal rho of the, rho of the volume, right? Let's make this type of volume equal to constant. So when rho equal to constant and dm to constant, so which means that this d volume has to be 0. dm has to, I make a mistake here. So dm has to be 0 because there d means changes, differential, right? So from the mass conservation, we know that there's no mass change, so dm has to be 0. And then dm can be rho of dv, right? So dv has to be 0. And dv means that 0 means that there's no volume change because rho equal to constant, right? So which means that v has to be constant. There's no change of the volume with time. And other way, okay, there's no change of volume with time is this one. So this is delta v. Okay, so v equal to constant, telling us that this is delta v equal to 0. Okay, so in another way, it's showing us that when you have incompressible flow, this dilation rate has to be equal to 0, because that when you have constant density, you won't have any change of the volume for the fluid particle. This is one way we can do it. Another way we can do is that for incompressible flow from mass conservation, what's the mass conservation form of incompressible flow? Remember what's the mass conservation form of incompressible flow? This is conservation mass. Okay, for incompressible we have this one. This is what from the definition we have. We also call this rate of dilation, right? So yeah, so this is as this is the this result conclusion we get here agree with the mass conservation equation we got for the incompressible flow. So in another word, okay, this dilation rate of rate of volume dilation, okay, basically this basically is the divergence of the velocity vector. This divergence of the velocity vector showing you that so this divergence of velocity vector showing you that whether or not the flow is compressible or not compressible. Okay, so for incompressible flow, so this has to be equal to 0. Okay, and we also have an example for the for this linear deformation. Okay, and in this cases, okay, the velocity field is given by this one. We have the x direction velocity and y direction velocity. X direction velocity is ax, y direction velocity minus ay. So this is a flow field near a corner. Okay, and why this is flow field near the corner, you can look at the example 5.4 in our previous lecture. Okay, and a is constant is given by 0.3. Okay, and we also have 4 points here given their position at t equal to 0. We given here, and we want to see that what's the new location with this 4 point after this point A is moving to x to 3 over 2. Okay, so to do this, first thing we need to find that for this A point at t equal to 0, A for this A point x equal to 1, right? And later on x will become to 3 over 2. We need to find out how long, what the time span, what this time interval tau will be. Okay, the first thing we need to find that. Okay, to do that, we need to track this particle A here. Okay, when we track this particle A, basically it means that we are using a Lagrangian method. Okay, so we do this by the velocity field. Okay, so the u velocity of A, the u velocity of flow particle is given by dxp over dt, and then this u is also given by this local value. This x here is not this x here, you must replace the x with xp, with the particle at this moment was this particle position xp. Okay, so this is the u velocity. And similarly for the v velocity, will be dyp of dt, and will be given by this minus a of y, and you need to change this y with yp, the particle, the y component, the y location of this particle at this moment, specific moment. Okay, and this is an ordinary differential equation. This is an ordinary differential equation. You can integrate this equation on the time, okay, from 0 to tau, and then x, this xp from 0 to x. Similarly for this one, you can integrate on time from 0 to tau, and then for y it's from 0 to y, right? So that after you integrate it, you can get that, you know, for the particle, fluid particle s of p, okay, as a function of time. For the fluid particle y of p as a function of time, tau. Okay, and this x0, y0 is at t equal to 0, what the x value and y value will be. So with these two equations here, okay, this is so this give you like xp as a function of xp of tau, right? So this one give you y of p as a yp of function of tau. So this is these two equations give you the Lagrangian description of the flow particle, the position of the particle. Okay, and now we know that you know, for xp for this particle A, right? When x equal to, when tau equal to 0, x0 is 1, and when t equal to tau, we get you know, x equal to 1 to 3 over 2. So by this way we can calculate what this tau value will be. They're telling us that okay, the time interval will be 1.35 seconds. And after you know that this tau value 1.35 per second, you substitute to these two equations for all these four particles A, B, C, D. So you can find that after tau equal to 1.35, what their new x will be, new xp, new yp will be, new location will be, right? So it can be given here. Okay, so this is the new location. Okay, after t equal to tau for all these four particles. So if you draw it, we can draw that A prime, B prime, C prime, D prime for this flow. And what do you see here? So for this new location, you can see that for this flow it only has linear deformation. There is no angular deformation for the flow, and also the flow has no rotational motion, right? Because that you can see that flow particles they are not rotational. Okay, only have the linear deformation for the flow problem. Okay, and the rate of the linear deformation on the x direction is given by this partial u partial x, and substituted, you know that is 0.3 per second. It's larger than 0, so that means that on the x direction is stretch, right? And the rate of the linear deformation on the y direction is partial v partial y, and you get it negative 0.3. Okay, so that means that on the y direction actually is contracted. Okay, and so the volume dilation is basically, you know, the divergence of v, you get it equal to 0. Okay, so which means that flow is incompressible. There's the area here and the area here is same. Even they have the, you know, linear deformation, but you won't change the area inside of this fluid particle. Okay, and similarly you can calculate the you know, the omega value if you want. You find the omega equal to 0 for this case. Angular you can also calculate the angular you know, deformation on this xy plane. You will also give it showing you that the angular deformation is equal to 0 if you want. Okay. So this is an example showing you how to the linear deformation. And now we finish all the you know, the kinematics description for the fluid, the motion of the fluid particle. We knowing that how to using the velocity field to calculate the linear acceleration of the particle, to calculate the rotational speed, the rate of rotational motion of the particle, omega, you know, and also we can knowing that how to using the velocity field to calculate the angular deformation and the linear deformation of this fluid particle. Okay, and now we can go to the momentum equation, right? And what is the momentum equation? Momentum equation is the Newton's second law. Okay, df equal to dm times the a times the dA, right? And so this is the differential force. So this is the force working on this differential particle, fluid particle, and this is dm is the mass, and this is dv over dt. So this is the d of a, not d of a, sorry. So this is A of P. So this is the acceleration of this particle. And the acceleration of the particle from our previous knowledge, the accelerated particle is given by this dv of dt. This is total acceleration of the particle, right? So you substitute that the total acceleration of the particle with the material derivative. Sorry, let's go back. Okay, you substitute this AP with this total derivative of the velocity field, which will be u dv dt dx, v dv dy, plus w dv dz plus dv dt. You substitute this AP with this one. This is what we got before, right? We know that AP equal to this one will be equal to this one, okay? And then also remember that this dm can be read as this rho times dv, right? Rho dx dy dz. Okay, so this can be read further in this form, okay? So this will be our Newton's second law for this fluid particle. Now we are looking we know the motion, right, from the velocity field. Now we need to know that what is this force, right? So what will be the force acting on the fluid particle? Based on what we have before, right, we can make we can look in this force into two groups, right? One is the surface force and one is the body force. For the surface force, we also calculate the stress force, and we have two kinds of stress. Remember, stress is a force per unit area, right? We have two kinds of stress. We have the shear stress and normal stress. Okay, and let's take a look at this particle. Let's looking at what's the overall, what is all the stress force on the x direction. We're only looking at the x direction force. Okay, so we are on these two surfaces. We will have the stress for normal stress force on x direction, and on the other four surfaces we will have the shear stress force on the x direction. Okay, and assume that we know that this sigma xx is the normal stress force at this center point, and this tau yx, tau zx, these two shear stress force on this center point. And using the Taylor series, we can calculate what the normal stress force on this left and right surface, and also what is the shear stress force on this bottom and top and the front and end surfaces. So we have all these 6 components of the stress force on the x direction, right? So what's the overall total surface force on the x direction? You just add all these 6 components together. Okay, add the sigma, add this one, add this one, add this one, this one, and this one, this one. Add them together, some terms will be cancelled, and the only thing left is this one. So this will be the overall surface force on the x direction. Partial sigma xx, partial x plus partial tau yx, partial y plus partial tau zx, partial z times dx dy dz. Okay, and this is only about surface of x direction. And let's also add the body force on the x direction, so rho of gx to it, so we can get the overall net force on the x direction. It contains this dfx contains contribution from the both body force bx on the x direction and the surface force sx on the x direction. And similarly, you can calculate what the net force on the y and z direction, dfy and dfz. Okay, they will have the similar form. And substitute this force back to this Newton's second law to replace this F on x direction, y direction, and z direction. And we can get the overall momentum equation in the differential form. Okay, so this is the overall of the final equation. The left-hand side is the force. The right-hand side is the change of the momentum, right? Or in other words, that dm times a. Okay, so this is so we have 3 equations because it's the momentum equation. So this is the differential form of momentum equation on the x direction, differential form of momentum equation on the y direction, and differential form of the momentum on the z direction. Okay, and our next task is to find what this stress for terms it will be: sigma xx, sigma yy, sigma zz, and also the tau yx, tau xy, tau yz tau xz, tau zx, tau yz, tau zy. Right? We have 3 normal stress and 6 shear stress. We need to find what they are. And how to find this stress will depend on what kind of fluid you have. Right? Remember that when we're talking about the Newtonian fluid and non-Newtonian fluid earlier in the section 2 and in the chapter 2. Okay, and if you have different kind of fluids, you will have different way to calculate this kind of stress. And we know that the most simple fluid is Newtonian fluid, which is also the common fluid we have in our daily life. Right? So let's take a look of if the fluid is Newtonian fluid, what we do. Right? So if in the Newtonian fluid, okay, we can calculate this tau xy or tau yx in this way. Okay, and similarly we can calculate tau yz, tau zi, tau zx, tau xz in this way. And for the normal stress, we can calculate it. It will have the contribution from the pressure force, and also has a contribution from this dilation. The dilation, because we know the delta V equal to 0, it means the dilation equal to 0, right? The rate of dilation, and also another term here we call it the we call this kind of correlation constitution correlations for the Newtonian fluid. Okay, and you may ask me, right? Before we have this tau yx equal to mu partial u partial y, right? And y now is tau yx contains both u contribution and the v contribution, not only partial u partial y, not partial v partial x. And because this is because that previously when we seeing tau yx, that is only the flow is only have the u velocity and has the gradient on the y direction. Okay, and in another word, that flow motion is only one dimensional. And now this tau yx, tau xy, we consider that this flow motion in the 2-dimensional, both on the u and v direction. So you need to have another contribution from another dimensional flow motion. Okay, and similarly for tau yz and tau zx. Okay, and actually how we get these correlations here, you see that this 6 correlations, right? These 3 correlations for these 6 shear stress, and these 3 correlations for the 3 normal stress. And how we derive this actually is is out of the scope of today's class. Okay, basically you will learn how we get this in the MEC 394. Okay, so where is like we will talk when we're talking about more details about this viscous flows, you will knowing that how we get this. Okay, right now you're just thinking about that this is given. Okay, this correlation is given to calculate. So this is how all the correlation, how to calculate these stress terms in the Newtonian fluid, in the 3-dimensional Newtonian fluid, in the rectangular coordinates. Another thing you need to know is that this tau yx, tau xy, actually they are symmetry. Okay, you see the tau xy is tau equal to tau yx, and tau yz equal to tau zy, tau zx is tau xz. Is they are symmetry because that the mathematical form here. It doesn't matter that this one add this one first or this one add this one first. You get the same thing. So that's why this is the symmetry. Okay, and we usually can write this stress in a tensor form, so that we write sigma xx here, sigma yy here, sigma zz as a diagonal term, and tau xy, tau yx, tau xy, tau xz, tau zx, tau yz, tau zy. So by writing this tensor form, you can also knowing that this each component is also symmetry in this tensor. This one is same with this one, this one is same with this one, this one is same with this one. All right. Okay. Anyway, so you just substitute all these stress terms for this Newtonian fluid into this sigma x, sigma y, sigma zz, all these tau values into this different form of momentum equation, and you will get this final equation here. So this is the rho. This is the change of the momentum, right, on the x direction, on the y direction, on the z direction, and this is all those force term. Okay, and this very complicated equation we got obtained is just called the Navier-Stokes equation. This is the most famous fluid equation in the fluid mechanics. Okay, And the Navier-Stokes equation we derived here is the general one. It's working for if mu is not constant, it's still working because this mu is inside this derivative. Okay, and if the flow is not compressible, it's still working because we have this we including this dilatant term. All right. So this equation you can see that is very complicated. Okay, it's almost not possible for us to solve, analytically. Okay, so let's consider two simple cases for this Navier-Stokes equation. The first case is let's consider an incompressible flow with constant viscosity. Incompressible flow, what do you mean? Incompressible flow means that this is go to zero, this go to zero, this go to zero. Because we know that for incompressible flow, the rate of this dilation equal to zero, right? We just mentioned it before. And also for mu equal to constant, we can take this mu outside. We can take this mu outside. We can take this mu outside, and so on. After you do that, and you can regroup your governing equation, your Navier-Stokes equation in this form. You can see that this Navier-Stokes equation, which is called the Navier-Stokes equation for the incompressible flow and with constant viscosity, this looks much more clean and much more simpler than the previous one. Okay, let's make the problem even simpler. Okay, not only constant viscosity, let's assume viscosity is zero, which means that the flow is inviscid. There is no viscosity, like mu equal to zero. So that this term is gone, this term is gone, this term is gone. And the only thing left is here. And we can rewrite this in this vector form. Rho of dv dt, total derivative here, will be rho of g, this three term, minus the gradient of p, this one. So this will be the form Navier-Stokes equation for incompressible inviscid flow. So the problem become even, even simpler. Okay, basically just this equation here. This is three equation without this viscosity terms. Okay, and this is called the Euler's equation. Okay, and this is actually the momentum equation. Actually, we are going to use in the next chapter. Okay, on the chapter 6, we are going to focusing on the this incompressible inviscid flows. So basically, this is the momentum equation we are going to use to solve the flow problem. All right, and so this is we're doing a lot of work here, to try to study the kinematics of the fluid particles. But our final target is try to find this momentum equation, and it turned out that that's why we got this Navier-Stokes equation. Okay, and we also have sample problem, two sample problems to working on this Navier-Stokes equations, and I will go through this together with you guys on next Monday's class. Okay, and here I would like to just finish today's lecture here, and please try to watch this video. Okay, and if you have any question, you can ask me the question on next Monday's class. Okay, and on Monday's lecture, we will also try to quickly go through what we learned here, so that if you have any question, you can ask me. All right, and that's it. And happy weekend, everyone. Okay.